Here's our example problem this morning. We have a plate, thermal conductivity K. We have the left-hand side kept at constant temperature T1. The bottom kept at constant temperature T2. And we also have the right-hand side is perfectly insulated or adiabatic. The top has convection heat transfer to a fluid at T infinity with a convection coefficient H. Now, we're going to set up the governing, we have some help over there for you. We have to set this up, and we go back to our original equation. Now, look at the axes, X and Y, 2D heat conduction. Did I specify any internal generation of energy, Q dot term? No. Did I specify time anywhere? No. Steady state. So we have steady state, no generation. We're assuming that the properties are constant, not a function of time. K is a constant. So here's our equation. Is temperature a function of X? Yes. From the picture. Is it a function of Y? Yes, from the picture. Is there Q dot? No. Is there anything varying with time? No. Conclusion, this then is our governing partial differential equation. Second partial T with respect to X plus second partial T with respect to Y equals 0. Okay. I don't need an initial condition. This is not a time varying problem, but I do need boundary conditions. So I need 4 of them. Here's why. Second order time, temperature and X. Second order temperature and Y. So I need 2 BCs relating temperature to X and 2 BCs relating temperature to Y. Okay. BC number 1. I know when X is equal to 0, for any Y value, the temperature is T1. So temperature is T1. T at X equals 0 for any Y equal T1. At the bottom of the plate, I know when Y is equal to 0 for any X, T equal T2. I know the right-hand side's perfectly insulated, adiabatic. I know at the top of the plate, convection heat transfer occurs. That's case 4, table 2.2. Convection boundary condition, case 4, table 2.2. Now, that's how the problem is properly posed. When the problem's properly posed with the governing PDE and the boundary conditions, theoretically, we can solve it. And if we could solve it, we'd get temperature as a function of the 2 variables X and Y. And then we could find heat transfer, Fourier's law. But the first step is always to find the temperature distribution in conduction. We do that by going to the governing differential equation with the correct initial and boundary conditions. Once we get the temperature as a function of whatever it might be, x and y, maybe time, then we can use Fourier's law to get heat transfer at some point in the particular object. Okay, now, I'm going to take another problem. Your homework Monday has two problems similar to this, so I'm going to work just because I think it might help you when you're working homework for Monday. It's a problem taken, it's an example problem out of the textbook. It's example problem 2-3. Once in a while, I'll do that. I'll take an example out of the textbook because maybe it's a little more involved. I want to make sure you understand how to work it. Maybe it will help you in homework, so I'll go through it in more detail in class. So I'll do that sometimes. Generally, I'll work end of chapter problems, similar to homework. But once in a while, I'll work in chapter example problem. This problem has a wall 1 meter thick. So here's a wall. K for the wall. It's 1 meter thick. And we're given the wall properties, density 1600. K is 40. C sub P 4,000. So kilograms, cubic meters. We're also given, there's some heat generation in the wall. There's Q dot. Q dot's 1,000. And let's see, okay, the last thing we're given is we're given the temperature distribution. Temperature in degrees C, 900 minus 300x minus 50x squared. So they give us the temperature distribution in the wall. So somebody had to solve a differential equation to get that. We don't know how. He gave it to us in that problem. So fine. For two of your problems for homework, they also give you temperature distributions. I take that back. Maybe 3 of the 4 problems they do. I think maybe 3 of the 4 problems they give you the temperature distribution. So what we're doing here will be very similar to your homework. And we're asked to find the heat transfer. So find Q into and out of the wall. We're also asked to find the rate of change of energy storage in the wall. Okay, so that's what we're given. Now, I think we also maybe know the area. Let me double check that. Yeah, the area is 10 square meters. Okay. Thickness is 1 meter. All right, so let's do part A. Q in the wall. We're going to assume that's x equals 0. A problem like that, it might be good, first of all. I mean, how do I know those directions are right? They're both going to the right, Q in, Q out. Is that correct? Well, the way you find that out, let's plot the temperature. There's a temperature as a function of x, so go ahead and plot the temperature. So here's the temperature. Here's x. 0, 1 meter. X equals 0, 900. X equal 1, 550. It's not linear. I'm going to exaggerate it greatly. Looks like that. Now, we know what heat does. It flows in a direction of decreasing temperature. Look at the left-hand wall. Yep, temperature's going down, heat's flowing in. Got it, arrow that way. Right-hand side, temperature going down, heat conduction that way. Yep, I got it right. So now I kind of understand what's going on in a way. But I want to find that heat transfer in. So I go back to chapter 1, Fourier's law. Q equal minus Ka dt dx. Where? At the location in. And where's that? At x equals 0. Okay. dt dx equal minus 300 minus 100x. Okay, there's my dt dx. What does it say? It says put x equals 0. Okay, good. dt dx is minus 300. So minus K, 40. Area, 10. dt dx minus 300. 120,000 watts. Plus, sign is plus, and I told you what plus means. A plus Q means the heat goes in the plus X direction. Yeah, there's the arrow. Yeah, I know that. That just checks and confirms for me I'm doing things correctly, sign-wise. Q out equal minus K A dt dx. Where? At x equal L. What's L? 1. Minus 40. Area, 10. Now, put x equal 1. Minus 300 minus 100 is minus 400. 160,000 watts. Okay, so more heat's going out than's coming in. So you can guess what's happening. The thing's getting hotter with time. It's getting hotter. Okay. Now we'll do part B. Okay, the rate of change of energy storage in the wall. Chapter 1, energy balance on the wall. Okay, I'll put it right here. E dot in minus E dot out plus E dot gen equal E dot storage. Okay, there's no generation, 0 generation. So E dot, put that in here and solve for E dot storage. Minus 3,000 watts. 30,000, pardon me, 30,000 watts. Or you can use that guy, K d squared t dx squared plus q dot equal rho cp dt d time. That's what you want right there. Okay, that guy's in watts. That guy's in watts. You get the same answer. So your choice, you can go back and use the energy balance on the wall to get the answer, or you can go to that equation right there. By the way, I guess I didn't mention, but let me mention what this equation means in words. This term is the net heat conduction in the wall by, in the x direction, the net heat conduction in the y direction, plus the energy generated inside the control volume is equal to the net rate of change of energy storage in the control volume. That's what it means in words. Okay, so you got, just so you know, now this is an interesting problem because you use chapter 1 here, chapter 1, Fourier's law. You use chapter 1, energy balance on the object, or maybe you want to use chapter 2, the heat diffusion equation in terms of x. So it's your choice which one you want to do here, either way. Okay, so that will help you, I hope, on your homework then. Now, that pretty much wraps up chapter 2. It's the shortest chapter in the whole book. Now we go to chapter 3, which is one of the longer chapters of the whole book. Okay, so let me start chapter 3. I'm going to save this for the next class, so I'll erase this. Uh-huh.
You said there's no heat generation in that problem?
Yeah, here it is, Q dot. There it is. That's why. Oh, okay. Sorry about that. Thank you. Thank you. There sure is. I got ahead of myself. Good. Otherwise, those numbers don't come out to be.
And I have one other question.
Uh-huh.
If you were to use the equation that you wrote at the bottom,
Uh-huh.
the partial t with respect to x would be a function.
Here it is right here.
Oh.
Second partial, minus 300. I'm sorry, minus 100. This guy goes out. Second partial is minus 100.
Mm-hmm. So there's no x in it.
Mm-hmm. Mm-hmm.
Okay.
Mm-hmm. Okay, chapter 3. Okay, chapter 3. 1D heat. This is what chapter 3 has in it. We assume the part we're going to do first. We assume it's going to be 1D. We assume it's going to be steady state. We assume it's constant properties. And we assume there's no generation. We start out as simple as possible. That's as simple as possible. We're going to draw a very similar picture to this. Okay. We have, again, a wall. We have x measured from the left-hand side, x equals 0. The thickness of the wall is L. We assume the temperature on that side is T1, maybe hot. Temperature here is T2, maybe cold. We're going to have heat coming into the wall here and heat going out of the wall here. Just like other picture, but the difference in them, this one has a Q dot. This one has no Q dot. Make life simple first. So we do the simplest things first. Okay, wall, we got the wall. Yeah, we have the K value of the wall. That's fine. We're good, I think. Right. So now we start off and we write down the correct governing differential equation. Okay, we go over here. Follow these rules. Constant K, constant K. I already assumed constant K. This version of the heat diffusion equation has already taken care of constant K. We pull the K outside the partial sign and divide it through by K. Divide through by K, divide through by K. Okay, that's taken care of. 1D, okay. This term goes out, got it. Steady state, okay. This term goes out, got it. No generation, okay. This term goes out. So here we go. He's gone, 0. He's gone, 0. He's gone, 0. That's it. D squared T, dx squared is 0. So differential equation is d squared T dx squared equals 0. What's next? What's next? We want to find the temperature. We integrate it twice. You can write this equation if you want. d dx of dt dx equals 0. Derivative of something here is 0. That something has to be a constant. So dt dx equal a constant. Call it C1. Integrate it again. T as a function of x. C1x plus C2. Once I do that, I can see a very important conclusion. If all 4 of those assumptions are true, the temperature variation through the wall is going to be linear. Linear. So now I know. It looks like that. Linear. Okay. Now I'm going to find C1 and C2. Let's see. I'll do it over here. Let's just make this whole board okay. Okay, the boundary conditions. BC number 1. The temperature at x equals 0 equal T1. Okay, put x equals 0. So the temperature at x equals 0 is T1. At x equals 0, the first term goes out. Second term is C2. So now I know what the constant C2 is. It's temperature T1. BC number 2. I know the temperature at x equal L equal T2. Okay, plug it in here. T2 equal C1, but x is equal to L, okay, plus C2, but C2 is T1, okay. Solve for C1. Got it. So write the temperature equation out now. Temperature as a function of x equals C1 times x plus C2. Okay, so there's the specific solution now in terms of the wall thickness and the temperatures T1 and T2. Now that's the first object in a conduction problem, if you approach it from ground zero there, is that you want to find the temperature distribution by solving the governing differential equation. Okay, but the real object is I want to find the heat transfer. That's the real object. I mean, sometimes the temperature is important. For thermal stress problems and things like that, the maximum temperature in something you want to make sure you don't exceed. So yeah, it's important many times, but it's very important then once you get this to get the heat transfer. Okay, what's the heat transfer? Chapter 1, Fourier's law. Then Q equal minus K A dt dx. Now, this is the temperature, okay? So our temperature here, dt dx, he's gone. T2 minus T1 over L minus Ka T2 minus T1 over L. Our Q is equal to, I'm going to get rid of the minus sign, Ka T1 minus T2 over L. Okay. So now I've got two very important conclusions. I found the temperature distribution in the wall, and I found out how much heat transfers goes across the wall. Does it matter where you are in the x direction? Is Q depend on where my hand is here? No, it doesn't. There's nothing there about, I don't see an x in that equation at all. No, it doesn't matter. It's the same here, the same here. Why? It's a linear profile, that's why. Is the slope the same at x equals 0 as it's same at x equal L? Of course it is. It's a straight line. Okay, now I'm going to kind of rewrite that. Q equal T1 minus T2. Before I do that, T1 in my picture is bigger than T2. So this is going to be positive. L is positive. A is positive. K is positive. Gives Q is positive. Yeah, that's right. Which way does heat go in this picture? I didn't put arrows. Oh, I did. I'm sorry, I did. Sure it does. High temperature to low temperature. We know heat goes in. Look over here. High temperature, low temperature. Of course heat goes out by conduction. Of course those arrows are right. Are they the same? Is Q1 equal to Q2? Yeah, just call it Q. Just call it Q. Okay, rewrite it. Divided by L over Ka. And somebody said, gosh, you know what, that thing, it looks similar to this. Yeah, it looks similar to Ohm's law. Because the left-hand side, this is electrical current flow. This is heat flow. The drive, what makes a current in a copper wire? A difference in voltage. What makes heat flow? A difference in temperature. Yeah, the driving potential. This is called the electrical resistance. You know what? I'm going to call that the thermal resistance. Okay, so conclusion. If these four conditions are met, and only if they're met, can you say this? R conduction equal L over Ka. All right, let's box that guy in. Now, if the resistance is big, the heat flow is going to be small. Big denominator, small quotient, big. What makes the resistance big to cut down the heat transfer? L. The bigger L is, the smaller Q is. Okay, that makes sense. The thicker that wall, concrete wall over here, the less heat's going to flow through it. Okay, common sense. The bigger the area, the smaller the resistance, the more heat flows. That makes common sense. Sure, the bigger the area. If I make that wall twice as big as it is, There'll be more heat flow through there. Twice. Okay, got it. That makes sense. K, copper and concrete. I know which one conducts heat better. K for copper, really big. The resistance is going to be really small. If this is really small, that's really big. Q through copper, bigger than Q through concrete. That makes common sense. So the resistance does relate, to your thoughts, what should happen. Okay. Now you can then draw this like you did over here. We're going to draw this as a resistance. Here's the driving potential. T1 is big, T2 is small. This is our conduction. And this is the heat flow Q. That's our model for heat flow through a plane wall by conduction. Now, let's take another case. For convection. All right, Newton's law, chapter 1. Q equal H A T surface minus T infinity. Okay, Newton's law, chapter 1. So I say, you know what? I'm going to rewrite that guy. Q equal T surface minus T infinity divided by 1 over HA. Okay? And I'm going to say, you know what? That looks like Ohm's law. The flow of something, heat, equals a driving potential, a difference in temperature, divided by something like a resistance, like Ohm's law. So yeah, I'm going to call that guy our convection. Okay, and let's box him in. If I want to make the resistance small, I make the area, the surface area, large. And then more heat flows, obviously. If I want to make the resistance small, I make H big. To cool a surface, use water rather than air. Oh yeah, H for water over a surface is a lot bigger than H for air. So use water, make H bigger. Resistance goes down, more heat flows. That makes sense. So again, it makes common sense. And I show this as a resistance now, convection, between T surface, and then I have my T infinity, my free stream fluid temperature. Then I have my R convection. Then I have my heat flow by convection. I'm going to put that down. I'm going to put this down, Q conduction. So now we have two resistors we can use to model a wall. What if there was convection on this wall and convection on that wall? Each wall would have a convection resistance. And there's conduction in here. So now there's three resistances: a convection resistance, a conduction resistance, and a convection resistance. Question?
Yeah, so for the R conduction, you said that's only true if those assumptions are
Yeah,
true.
right.
Are there any assumptions for the R convection?
No, that's fine.
Oh,
That's
okay.
fine. Yeah. These are the assumptions in the wall or any solid like, but what's on the boundary, the surface, then don't worry about that. Yeah, you can use that. So obviously, what we're going to do is we're going to be combining these guys into plates with, this might be copper with insulation, copper wall, insulation on the wall, convection on both sides, 4 resistances, 2 conduction, 2 convection. So we'll be modeling walls like that. You want to model that concrete wall right there for analysis? Not a problem. There's a convection resistance with the air in this room. There's conduction through this solid concrete wall. And there's convection on the outside hall side wall. 3 resistances to analyze that wall thermally.